this thing called a population proportion. So when we're doing stats, ideally, we'd love to gather every piece of data that is possible. And when you've got every piece of data, that's the population. We call it population. And so if we had every bit of information and we gathered that, when we do that, that's what you call a census. All right, let's use this as an example. We've got a particular city, there's 1 million people in the city, and because this is something we'd really be interested in, that if we were to go up to them and randomly ask them for a number, that they would choose a prime number. I mean, important stats that you want to know. So we simply ask them to pick a number between 1 and 100. So the probability that they get a prime number, that's what we'd call the population proportion, the proportion of the population that picks what we want. By the way, I'm sure you knew this anyway, there's 25 prime numbers between 1 and 100. No, it's amazing. 1/4 of all the numbers from 1 to 100 are actually prime numbers. So 0.25. When I did a simulation of a census on this and just got them to randomly pull out, I ended up with 249,925 prime numbers. So I wasn't far off what I was expecting there, because when you think about it, that's what's that? 0.249925. That wasn't a bad little census. But of course, you can't predict what they're going to say. So it may not agree. Mine was very, very close, but there really is no reason why it should have been close, because it was just people picking random numbers. So sample proportion. To conduct a census is unrealistic, depending on the size of the population, I guess. The one I had was 1 million people, right? It can take too long. I guess that's why the Australian Bureau of Statistics only does their census once every so many years, because they're trying to capture every person in the country. The cost, you've got to employ people to do the census. Time consuming to then go and analyse every single piece of data. So in realistic terms, what we do is we sample, and that's when we call it a survey rather than a census. Now, ideally, and it's not always possible to do this, it's very hard, but ideally, the sample that you choose should reflect the exact same characteristics of the population itself. And as I say, that's not easy to do. I mean, your population, depending on what you're looking at, imagine the population had, 20% had blonde hair. Then ideally your sample should have 20% blonde hair. It's very hard to match it, but ideally that's what you'd like. So, okay, I went and surveyed 100 people from that city of 1 million people and asked them to choose a number. 29 of them ended up picking a prime number. So the sample proportion would be 0.29. Now, how do we distinguish between population proportion, sample proportion? Just with that little caret on top, so p hat, if you like. So if we have a binomial distribution, then the sample proportion is that. So the random variable becomes the random variable of the population, but divided by n. So the number of people in the population. So the probability then that our p hat is equal to x over n would end up then being the same as x equals x, which is our binomial probability. So the NCX, p to the power of x, 1 minus p, n minus x. The expected value then becomes p, because we're going to go x over n times the number, which is n, cancels out. So we would expect that our sample proportion is the same as the population proportion. That's what we'd like. The variance is a little bit different there. It's still p times 1 minus p, but we divide it by n. And that's all to do with, it's actually sigma squared. So we have to divide by another n to get the cancelling effect happening. So p hat is going to give us an estimate of the actual probability p. All right, let's have a look at this one. Now, I'll admit I made this one up, and so it kind of gets a bit strange along the way. But anyway, let's have a look at it. Prior to conducting our survey of 100 people, what I wanted to see was, is 100 people enough to be able to draw a conclusion about the population? So I went and ran 50 simulations using the spreadsheet and the number of primes produced in the spreadsheet. So p hat is going to be the proportion of people choosing a prime number. So there's my 50 simulations and what p hat turned out to be in every one of those simulations. So some of them were good, some of them were bad. The expected value, of course, is 0.25 because that was the population one. But remember, there are 25 prime numbers less than 100. So that's why it's 0.25. So you can see there was, well, there's one there. Is there another one that's 0.25? Might have only been just one, was there? The variation, what we would be expecting for the variance then is 0.25 times 0.75 divided by the population size. So 0.00375. So we're not expecting a huge spread. So let's say I'm happy if my estimate is 5% of the actual value. So P, remember, is 0.25. So what I'm saying is I would like my estimate to be in between 0.2375 and 0.2625. So P hat, remember, X over size of the sample, 100. 23.75 then goes in between X. So in other words, that's what I'm saying. I would like the prime numbers to be in between. They choose 23.75 and 26.25, but hang on, I'm dealing with a discrete population here. I know I'm not going to get 23.75. So I'm going to push it out a bit and say, okay, 23 and 27. That's binomially distributed. I know that there was 100 in there and 0.25 is our probability. So I could add up all these and I get 0.43601. So there's a 44% chance that my survey will produce an estimate within 5% of the actual results. Is that good? Is that bad? But here's the interesting thing. Let's say I turned it into a normal approximation. Okay, so P is 0.25. P hat, I want to go between those. I'm not going to worry about pushing this one out because I'm going to make a normal approximation. Deviation turns out to be 0.0612. So I want my Z-score to be in between. I'm using absolute value because it's symmetric here, that boundary. 0.2625 minus 0.25 over the 0.0612. Look what it turns out to be, 0.1618. So it's now saying there's a 16% chance. I guess what I'm getting at is, remember I just said I randomly did this. Clearly, this was not a good one to do a normal approximation for. Those differences are huge there. Well, that happens. Not every distribution is appropriate to be a normal distribution. But what could I conclude? Certainly if I use the normal approximation, that sample size of 100 is not great because I ended up with a 16% chance and maybe even that 44% chance wasn't good enough. All right, that's my crazy example. Let's look at some more reasonable ones, more likely about what you might get asked. A recent census has showed that 20% of adults in the city eat out regularly. So a survey of 100 adults in the city is going to be conducted. We want to find out the proportion who eat out regularly. First thing they've asked us to do is show that the mean and standard deviation ends up being that. So, okay. Well, the mean would be the probability. That's what we're expecting. So 0.2, they're telling me 20%. So that's how I get 0.2. Really hard for a show that question because you're tempted just to say, well, they told me, well, 20% is 0.2. How do I just write 0.2 down and I haven't just cheated? So that's why I've said mean is P and that's 0.2. So I sort of showed how I got it. The deviation's a bit easier to show because I can put it into that formula and we get 0.04. Okay, they've given us a bit of a table then. So we're just going to turn it into a normal distribution and standardize it to get our answer. We want to find at most 15. So Z has to be less than 0.15 minus 0.2 over 0.04. 0.15 because 15 out of 100 is 0.15. So it put minus 1.25 on our table. Well, our table's only got positive numbers, so I'll go 1 minus 1.25. So there's 1.2, read across to 0.05. And we've got 1 minus that is 0.1056. Okay, so really that's the sort of thing that we might get asked. An online retailer claims that 90% of our orders are shipped within 12 hours of being received. Now, on a particular day, 121 orders have been received, and 102 of those were indeed shipped within 12 hours. So what's the sample proportion, so not the population proportion, but the sample proportion of the orders shipped within 12 hours? Well, our sample is the 121 orders, 102 of them were shipped, 102 over 121, 0.84, 84%. Not quite the 90% that they're promising. All right, well, the distribution is approximately normal. So they're telling us we can assume it's a normal distribution. Assuming the retailer's claim is true, find the probability that if we had a random sample of 121, so not the ones that were actually shipped, but if we were just randomly to pick 121 that have been shipped over the weeks, that less than 85% are shipped within 12 hours. See, they're claiming 90. We got 84. We want to see what actually is the chance that it was less than 85. Did this happen by chance or actually no? Their claim's not true. So our estimate would be the 0.9, because they're telling us 90%, that's what it is. Work out the variance, and a very, very small one, 7.438 times 10 to the negative 4. We're assuming it's a normal population, so 0.9 is the mean, and that 7.438 times 10 to the negative 4 is the variance. We're saying, what's the probability that our sample population was less than 0.85? Turn it into a z-score. We're saying z is less than minus 1.83. Again, I've got to turn that into a positive, and we get 0.0336. What is that telling me? Well, this is what part 3 wants us to say. Using that, how reasonable is their claim, that 90%? Now, what part 2 is telling me is there's a 3.4% chance of shipping less than 85% of orders within 12 hours. So there's only a 3.4% chance that that happened randomly. Our sample proportion was 84%, remember. So what we're now saying is that that result that we came up with, 84%, would have only occurred by chance 3.4% of the time. Well, if it's only occurring by chance 3.4% of the time, then their claim that 90% will be shipped has got to be wrong, because that didn't happen by chance. If it's only 3.4%, that's saying, hey, no, this is normal. That did not happen by chance. So their claim is dubious at best. So that example again is a little bit more involved. Look, let's look at the HSC one from last year. So we've got a factory, faulty items produced by a machine. The population proportion is 3 over 500. That's considered to be acceptable. So they want to see if their machine's working the standard. So a sample, we don't know the size of the sample, N, and they're going to work out the sample proportion, P hat. We can assume it's normally distributed, and so the average would be, well, we're assuming that it's going to be the population proportion and the data. So basically they've given us the formulas. Production by this machine will be shut down if the sample proportion is greater than or equal to 4 and 500. Now the sample size is going to be chosen so that the chance of shutting down the machine unnecessarily is less than 2.5%. Find the approximate sample size required, giving your answer to the nearest 1,000. Now you'll note there is no parts to this question. 14D, so I'm pretty sure that was the last question on the paper. Involves a bit more thinking. But basically you've got to put it all together. So what do we do? Well, I'm just going to write down what I know. The sample proportion, they've told me I can assume it's normally distributed. The average is 0.006, because that's 3 on 500. From that, I can work out the variance. I just don't know what n is. But I know it'll be 0.006 times that. I didn't bother writing that number down because it's going to have too many zeros and whatever. I just left it as those two things multiplied together. I'm going to turn that into a standard normal distribution. Just reminding myself there's the z-score. So it'll be p hat minus the average over the deviation. We're saying when is, where is it? P hat greater than or equal to 4 and 500. So we want to know what is the probability that it's greater than or equal to 0.008. We want to know when is that probability less than 0.025, because they told us. We want to know when is it less than 2.5%. This is what we have to solve. Again, I haven't bothered working out the numbers. I've left them there as a multiplication, but essentially that's what we're trying to work out. When is Z greater than that? Less than 0.025. Now, if you look at your empirical formula, again, 0.025 is quite a significant number because 2 deviations from the mean. We're essentially saying when is that number greater than 2 deviations from the mean. Right? So it's come from that empirical formula looking at the curve. So again, we didn't need a table to do this one. Well, it's just manipulation now. We end up with n's greater than 5,964. So they said how many to the nearest 1,000. So we would need a sample size of approximately 6,000. Does it ever stop? The fun never stops. Stephanie.